This is a video teaching the concept of complete the square. And so in order to understand the complete square, I think it's helpful to understand where the name comes from. So the idea is that what we're trying to do is take a polynomial function that is not a perfect square and, in a sense, complete the square. So make a perfect square polynomial out of the polynomial that's not a perfect square. So here I thought we'd start with some examples of perfect squares. These are all perfect square polynomials. If you were to factor them, this would factor into x and 3 and 3 plus plus. So in other words, we could write it as x plus 3 squared. That's why they call it a perfect square polynomial, because it can be factored into two terms that are the same. Likewise, this you could factor out the 4 first and make it easier to factor. And when we go ahead and finish factoring this, we'll factor into x plus 1 squared, won't it? This one here, maybe a little bit harder to see. So I'll do that from scratch again. X and x, that would be 1.5, 1.5, and plus and plus. Now normally when we're factoring, we don't usually use decimals, but if we're trying to get a perfect square factor, we actually can do decimals. So that's why I wanted to show that one. Because you notice that 1.5 times 1.5 is 2.25, and 1.5x plus 1.5x is 3x. And of course, x times x is x squared. So these are all examples of perfect square polynomials. We could do a few more. They're pretty easy to generate because they all have the same characteristic. If you take the b term and divide it by 2 and square it, you'll get the c term. That's always true of perfect square polynomials. So notice that half of 10 is 5, 5 squared is 25. Half of 18 is 9, 9 squared is 81. Half of 3 is 1.5, 1.5 squared is 2.25. And so if you recognize the perfect square polynomial, you can actually factor them really quickly because you know that it's going to be x plus just half of that, or the other way to think of it is the square root of that. They produce the same answer, 5. And same way here, this would be x plus 9 squared. So our goal in completing the square is to take an equation like y equals x squared plus 6x minus 4. That is clearly not a perfect square polynomial because half of 6 is 3. 3 squared is not negative 4. So what we want to do is create a perfect square polynomial. Now the purpose of this is you could use it to solve, so we can set this equal to 0 and use it to solve, or the other purpose is to take an equation in standard form and convert it to vertex form. And the complete square helps us do that. Okay, so the idea is, first of all, I'm going to clear out. I'm going to take x squared plus 6x and try to isolate it and put the little minus 4 on the outside, because now I have room to create my little perfect square polynomial. So I've set up a little environment that I have control of. The minus 4 is just sitting out there. Notice it's still a part of the equation. I haven't changed anything. So what I want to do here is, if I wanted this to be a perfect square polynomial, I have to take half of the 6 and square it, and that's what should go there. So half of 6 is 3, 3 squared is 9. So if I put a plus 9 there, then I have a perfect square polynomial within the parentheses. But I can't just put a plus 9 in anytime I want to. So to make it legal, I'm going to put a minus 9 out here. So notice that positive 9 and negative 9 still equals 0. So I haven't really done anything to the equation as far as change the value of it. It just looks different. So then my next step is to go ahead and combine these. That would be, of course, negative 13. And I'm going to take this and factor it. But it's not a long, complicated factoring problem because I already know I created a perfect square. I know that this has to be x plus 3 squared. I created it to do that. And notice suddenly it's in vertex form. So we took an equation here in standard form. I could not just look at it and pull out the vertex. But now that it's in this form, I know the vertex is located at negative 3, negative 13. Just by looking at it. So that's completing the square. Now I want to do another example because it does get more complicated when you have a number out front, like say 2x squared plus 6x, say plus 10 or something like that, I don't know. So once again, I'm going to create my little space, but it's a lot easier to think of how to make a perfect square without a number up front here. So I'm going to start by factoring out a 2 and leave it outside of the space that I'm trying to create for my little parabola, my perfect square parabola. And I'm going to kick the 10 out again too. Notice I didn't divide 10 by 2 because it's not inside the parenthesis. So in other words, what I'm saying is everything inside this parenthesis has a times 2 attached to it. Okay, so still I'm going to create my perfect square polynomial in here. So half of 3 is 1.5. 1.5 squared is 2.25. So there I have a perfect square polynomial inside the parenthesis. But again, I've added something that I can't just add it anytime I want to, so I have to counteract that. But notice that I didn't add 2.25. I actually added 2.25 times 2, because this 2 is attached to whatever goes on inside the parentheses. So what I need to subtract out here is actually 4.5, because that's what 2.25 times 2 is. So I'm trying to counterbalance what I did here. And now I'm ready to consolidate it. So I'm going to factor that thing. That's going to be, of course, x plus 1.5 squared. And this would be what? Plus 5.5. And we've got a nice parabola in vertex form. I can see the vertex looking at me. That looks like negative 1.5 comma 5.5. And we also see the stretch factor sitting there. It's twice as tall as normal. It's been stretched vertically by a factor of 2. And that is completing the square. Now, I want to do one other thing. Notice in this case that if I have trouble completing the square, or if I just want to check to make sure I did it right, all I really need to do is find out if I find the vertex, where the vertex is located, and I can see if this is working out right. So remember, if I want to find the vertex of an equation in standard form, there's this little formula, x equals negative b over 2a, that enables me to find the x-coordinate of the vertex. So if I do that, that would be negative 6 over 2 times 2, which is 4, and I get a negative 6 divided by 4 is, lo and behold, 1.5. Look at that. So notice it does check out. I did do it right. And if I wanted to check out the 5.5, I would actually plug that in up here. So that would be 2 times negative 1.5 squared plus 6 times negative 1.5 plus 10. And when I plug that in, I in fact do get 5.5. So it checks out. So even if I hadn't completed the square, I could write this in vertex form, because I know in standard form the 2 that I see out there is going to be also that is the stretch factor. So I know this would be 2 times something squared. And since I just found the x-coordinate of the vertex, that means this would have to be x plus 1.5. And I found the y-coordinate of the vertex, so it'd have to be plus 5.5. So it is possible to come up with the vertex form without going through the process of completing the square. And there you have it.